All right, we're gonna work through this review packet. Now, I will say that this is also my first time through the review packet, so we'll be coming across mistakes. We'll be finding them. We'll be talking through them. So let's just get started. Starting with vector addition, a vector has both magnitude and direction. So these two arrows both have the same direction, but they have different magnitudes. So magnitude is just the size of the arrow. Maybe this is 2, maybe this is 8. Those are different magnitudes, but the direction is maybe 20 degrees in both cases. Now, where is that 20 degrees matters. So for here, they talk about 20 degrees east of south. So let's see. Well, I know that south is this direction, and if I went a little bit to the east of south, that would be here. So my 20 degrees is what's between my main direction and my tilted towards direction. So mostly I'm south, and then I'm 20 degrees to the east of south. North, south, east, west. Okay. So the next thing to know about vectors is that you can break them into components, and that you need to before adding. So let's say I've got two vectors here. Let's say I've got a, let's say 40 degrees to the east of north, because I started at north and then I went to the east of north. So I've got 40 degrees east of north, and let's say I've also got 10 degrees west of north. Well, I can break these up and I can find the x component. Here the x component is going to be, let's see, that's the opposite. So I'm going to use sine of 40 degrees, but I need to know how long the arrow is overall, what the magnitude is. Let's make up a number, let's say 10. So I've got 10 times the sine of 40 will give me my x. 10 times the cosine of 40 will tell me my y. Over here, let's make up that this is a magnitude of 7, in which case my x, I guess I don't love that. My x is opposite, so I've got 7 sine 40 degrees. Y would be 7 cosine 40 degrees. Now, it's not always true that x is sine. That's not always true. They just both happened to be that angle. In a problem like this, here, x would be equal to 8 cosine of 20, because it's that part. It's the adjacent. Okay. Then when it comes to adding, I can say that my total x is equal to x1 plus x2, this number plus this number. Similarly, I can add y's, and my new y total will be this number plus this number. But I'm never going to mix x's and y's. I'm never going to do this 10 cosine 40 number plus the 7 sine 40, because x's and y's are like apples and oranges. All right. So that's kind of where this equation comes from. The sum of all the x forces balances to equal 0, and then the sum of all the y forces also balances to 0. That's specifically if it's in equilibrium, if it's not accelerating in equilibrium. So very similar to these questions, if I had a situation with a box hanging from cables, the first thing I would want to do is find the components, this x value and this x value, this y value, and then secretly the force of gravity is there as well. So in a problem that maybe looks like this, this and this both point up against this, so I'd have maybe like y1 plus y2 minus the force of gravity equals 0. In class, we would usually say FTY, FTY, just to make that look more familiar. All right. In the x direction, I only have these two things. So this x1 minus x2, let's say 1 and 2, equals 0. So x1 is the same size as x2. And any angled force gives both an x value and a y value. That's why we split it into the triangle. Let's see, F net equals ma. I agree. Consider the direction, right? We were saying left and right, up and down. Good. Yeah, constant velocity tells us that acceleration is equal to 0. That's a connection between the Newton's laws and the kinematics that we do later. If it's constant velocity, acceleration is 0. If it's constant acceleration, then a is not 0. It's just not changing. You know, maybe a would be 6 or something like that. A would be 12. Ooh, I almost said 7. That was close. All right, friction. Ooh, formatting needs to be improved. Anyway, that's supposed to say that the static force of friction, that its maximum is equal to mu s times Fn. And if I were to try to say a lot of things all at once, I would say Ffs is less than or equal to mu s Fn. Anyway, there's a maximum value, and it can't go beyond that value. So let's imagine a number. Let's say I knew this number, and I knew this number, and I calculated it, and I got 15. That means that if a person were to push this box that had a static friction of 15, if they push with 10, that static friction is going to push back with 10. If they push 11, then static friction is going to do 11. But if they do 16, the best that it could have done would have been 15. And so it'll start to move. Now that it starts to move, it is no longer static friction. And that's where we start to get into the other formula. The force of kinetic friction is equal to mu k times Fn. Friction will always oppose the intended motion. So if the person is trying to push this way, like if friction didn't exist and the box would have gone this way, friction will try to resist that. A lot of people fall into the trap and they think to themselves, oh, well, Fn is always equal to Fg. And so they'll falsify this statement and they'll say Ffs is less than or equal to mu times Fg. And that's wrong. Because sometimes for situations like when you're on a ramp or situations when you're being pulled up at an angle, Fn is not equal to Fg. So you have to be careful. The formula depends on Fn. Okay, this is talking about elevators. And then it said kind of the same thing like a bunch of times. So let's take a situation where I've got an elevator and the elevator is only at the top. So if I'm, not just falling to the ground, there's some amount of tension in this rope. If the object is slowing down while moving upward, well, really I don't so much care about which direction it's moving. I care about how it's accelerating. But I guess I do need to think about that a little bit. So if it's moving upward, but it's slowing down, that means it's accelerating downwards. Because it's accelerating downward, that means that the force of gravity is bigger than the tension force because it's always going to accelerate in the direction of the winner. If it's speeding up while moving upward, then my acceleration is upward. Upward is winning. So then my tension would be larger than my force of gravity. Lastly, if I'm at rest or at constant velocity, or acceleration is 0, these are the same thing, then my tension is going to be the same size as my force of gravity. One page down. Ramps. So, if I've got a box on a ramp, ooh, and I've got some formatting to clean up. Then my force of gravity is Fg. Fg is equal to mg. Now, here's one of the things I do advise students just to memorize. We can make a triangle out of the force of gravity, and we want a triangle that is perpendicular and parallel to this line. So I'm going to draw perpendicular. So these two are perpendicular, and parallel. And then this bottom angle is usually what they tell us. Let's say that theta is equal to 15 degrees. Well, that 15 degrees exists at the bottom of the triangle, and it also exists in that upper angle right here. Now, if I want to know how much gravity is pulling me down the ramp, Fgx is equal to mg sine of 15 degrees. It's sine because that's my angle, so I need the opposite. Now, if I want to know how much normal force there is, well, right now normal force is balanced with Fgy, so Fgy is mg cosine 15 degrees. If there's no friction, life's pretty straightforward. We'll just, like, there's nothing to fight it. This portion of gravity is the only thing pulling it down to the ramp. So F net equals ma. Whatever this number is gets set equal to ma, and that'll be our acceleration. But if there is friction, remember the formula for that would be static friction is less than or equal to mu times Fn. Let's say mu static, I'm just going to make it up. Let's say it was 0.2. My Fn is equal to my Fgy, so times mg cosine of 15. And you'd be given numbers, and so you'd be able to calculate, you know, something. For the sake of argument, let's just pretend that this was 30 newtons, and let's also pretend that we did our math and that this was 25 newtons. Well, if I'm only being pulled down the ramp by 25, but friction has the ability to resist with 30, then static friction is going to perfectly match, and the box won't go anywhere. So static friction would assume the value of 25 so that it could match, because it had the ability to go up to 30. All right. However, if it exceeded it, let's maybe flip-flop the numbers, so 30 and 25, then it does move. And now that it moves, I no longer care about static friction, so then I would have to do a kinetic friction calculation, mu k Fn. Let's say that I knew the values, and let's say that that came out to 27. No, that doesn't make sense. 20. In which case, I've got 30 pull down the ramp, I've got 20 resistance while I'm moving, and so my net force is equal to the 30 minus the 20, and so 10 equals ma, a equals 10 divided by m. Okay. Okay, yeah, I gotta format this better. So VF equals VI plus AT, D equals VIT plus 1/2 AT squared, VF squared equals VI squared plus 2AD. All right, now you guys have experienced by now that all these equations are true, whether I apply little x's to all of them, or if I apply little y's to all of them, they're just true. It's nice to know. Positive acceleration means you speed up. Negative acceleration means you slow down. There's some caveats to that. However, for pretty much any problem you do that's just a straightforward kinematic, that is close enough to true that I'll let you believe that. Okay? When we have a two-step kinematic, that usually means that there's a bigger picture going on, and I always have to draw a picture. A common question would be a person that, you know, has an acceleration for some amount of time, and then they change their plan, and then they have a different acceleration. Now, it could be that a equals 0, it could be that a equals negative, or it could just be that it went from a big positive to a smaller positive. The thing to be thoughtful about is that if the acceleration changes, I cannot treat the whole thing as one situation. Instead, what I need to do is I need to break it up into two portions. Portion 1 and portion 2. And things that are notable is that the VF of portion 1 is equal to the VI of portion 2. So if I solve stuff about this, it'll help me figure out the beginning of that. And vice versa. If I knew something about the beginning of this, that lets me work and know the end of that. Projectile motion, we've got a couple of things that we want to think about. My x's and my y's, again, are completely separate. The overlap, though, is time. Time will be the same in both the x and the y direction. AX is 0, AY is negative 9.8 meters per second squared. Boy, that sure does look ugly. If they give you a triangle where they give, 30 degrees above horizontal, which is the most common place that they would give an angle. It's pretty rare for them to give, from the vertical. So most times people give above the horizontal, so this angle. Now, if they do give us that, sorry, formatting, then this would be V, this would be Vx, and this would be Vy. And Vx would be equal to V cosine theta, Vy would be equal to V sine theta. Nice little trick. Yeah, the maximum height depends only on the vertical component. Whether you shoot faster sideways or slower sideways, that has no impact on how high it's going to go. How quickly it's moving at the beginning upward is what's going to determine how high it travels. I'm going to pause the video here, and then we will continue on with some practice problems in a moment. All right. Where's my mouse?